Now let's take another problem based on properties of pure substance. I am just writing the problem here. 2 kg of freon 12 is contained in a piston cylinder arrangement. The 20 mm dia 48 kg piston is is allowed to rise freely freely until the temperature reaches 110 degrees centigrade. Reaches 110 degrees centigrade. Calculate calculate the pressure. Calculate the pressure inside the cylinder. Inside the cylinder and final volume of the gas and final volume of gas. Take specific volume. Take specific volume of gas 0.014 meter cube per kg. I will again repeat the problem. Here 2 kg of freon 12 is contained in a piston cylinder arrangement. The 20 mm dia 48 kg weight is allowed to rise freely until the temperature rises 110 degrees centigrade. Calculate the pressure inside the cylinder and final volume of the gas. The specific volume of the gas is given, that is 0.014 meter cube per kg. So let's solve this problem. So if you see in this problem, the piston is allowed to rise freely until the temperature reaches 110 degrees centigrade. Means when the piston will rise freely and the one stage will come, then the piston uh, piston pressure means the pressure due to the piston weight and the atmospheric pressure will balance with the pressure inside the cylinder. So now I will just draw the diagram, then it will be very clear for our understanding. I am just drawing the diagram here. This one is the piston. I am suppose drawing the final stage where the piston is allowed to rise freely until the temperature reaches. Suppose temperature is now 110 degrees centigrade. So it's a equilibrium stage. It's a equilibrium stage. Equilibrium state here. Here we are having pressure here, that is P. Here we are having pressure, that is atmospheric pressure, and pressure due to this piston weight, that is W by K. So in equilibrium stage, this pressure atmospheric and pressure due to this W by K will balance the pressure P, that is inside the cylinder, gas pressure inside the cylinder. So now we can see that at equilibrium, I can write P equals to P atmospheric plus W by A. We know atmospheric pressure is 1 bar. 1 bar is nothing but 1 into 10 to the power 5 Pascal. So we know P atmospheric is 1 bar. And 1 bar is nothing but 1 into 10 to the power 5 Pascal. So here P atmospheric is 1 into 10 to the power 5. Similarly, we know the weight, that is 48 kg, and we know the area because dia we know. So area here, that is pi by 4 d square. D is nothing but the dia. Dia is given 20 mm. So I can write that is 20 into 10 to the power minus 2 meter. So area will be pi by 4, 20 into 10 to the power minus 2 square meter. So now I will plug all this value here. We have to find out P, that is pressure inside the cylinder. P atmospheric is 1 into 10 to the power 5 plus W. We know that is 48. It is mass, so we have to multiply it with acceleration due to gravity. A is nothing but pi by 4, 20 into 10 to the power minus 2 square. So now if you calculate this thing, it will come 1.6 into 6 Pascal. So we can say that 1.6 megapascal. So by applying the equilibrium state condition, we can easily find out the pressure inside the cylinder. Now we have to find out the volume of the gas. So specific volume of the gas is given and total mass of the gas is given, that is 2 kg. So mass of the gas, that is M is given 2 kg. Specific volume is given, that is 0.014 meter cube per kg. So now we have to find out volume. So volume will be mass into V. So 2 into 0.014. So volume will be 0.028 meter. So by this way we can find out the volume, that is 0.028 meter cube. So now let's take another problem. I am just writing the problem here. The pressure in a container carrying water is increased till it reaches critical state. The latent heat, that is HFG value at this point is, options are A 0.0046, B minus 0.0012, C that is 0.0084, and D that is 0. So now I will draw the TS diagram for our understanding of critical state. Here I am showing the temperature on y-axis and entropy on x-axis, and I am having this dome. Here we have already discussed. Here it is showing the saturated liquid, and here it is showing the saturated vapor, and this one is critical point. So now if the pressure in a container is increased, so I am just showing the pressure lines here. So this is constant pressure lines. So this one increasing pressure. This pressure is increasing, and here if you see it is like that. So now if you see a constant pressure line, suppose I am starting from here we are having a higher latent heat. If we increase the pressure for this, suppose here we are having less latent heat, here we are having the less latent heat, and if we come to the critical point, latent heat is 0. So we can say that latent heat value at the critical point will be 0. So correct answer is D, 0. Now take another problem. I am just writing the problem here. The steam is kept in the steam is kept in a container kept in a container and compressed. The product PV the product PV of steam when pressure tends to zero when pressure tends to zero when pressure when pressure tends to zero depends on depends upon A, that is pressure, B, entropy, C, temperature, D, enthalpy. So now we have to see the product PV. So PV, if we know the perfect gas law, then PV equals to RT. So here PV is directly proportional to T. If suppose the product PV, if we talk about, it's directly depending on T. So when pressure tends to zero, it will depend on temperature. So correct answer for this problem is C, temperature. Product PV of the steam when pressure tends to zero depends upon temperature. Problem that is very interesting. I am just writing the problem here. A pressurized can contains air at a gauge pressure of 10 megapascal 10 megapascal when the temperature is 40 degrees centigrade. the can will the burst can will burst at the pressure of 30 megapascal. So find at what temperature can will burst can will burst. So I am again repeating this problem here. A pressurized can contain air at a gauge pressure of 10 megapascal. When the temperature is 40 degrees centigrade, the can will burst at a pressure of 30 megapascal. Find out the temperature at which can will burst. So here I am solving this problem. So in this problem it is mentioning the can will burst. So bursting happen at a constant volume. So remember this thing, bursting happens at constant volume. So it's a constant volume problem. So for constant volume problem, if I write a perfect gas equation like PV equals to mRT. So for constant volume problem, I can write mRT by P equals to constant. So for this thing, I can write m r T1 by P1 equals to m r T2 by P2. Here m and r are the constant. So m and r is the constant. Only the T1 and P2 are the variables. So now I can simplify it. T1 by P1 equals to T2 by P2. And we have to find out the final pressure at which it is bursting. So we are interested in T2. So T2 will be T1 into P2 by P1. So T1 here it is mentioning at 40 degrees centigrade. So in terms of Kelvin, 40 plus 273, so it will come 313 Kelvin. And pressure, the gauge pressure P1 is given, that is 10 megapascal, and P2 is given, that is 30 megapascal. So now if we put this value T2, T1 we are having 313, P2 I am having 30 divided by 10. So T2 will be 313 into 3. So T2 will be 666. This one be in terms of degree centigrade. 666 degree centigrade. So in terms of degree centigrade, it will be 666 degree centigrade. So now I am writing the another very interesting problem. First I will write the problem. A mixture of CH4 and C2H6 with molar composition of 25 percentage of CH4 and 75 percentage of C2H6. C2H6 is compressed by reversible adiabatic process from 1 bar and 300 Kelvin to 10 bar. Determine the final temperature of gas. Final temperature of gas Cp for CH4 equals to 36.65 joule per mole Kelvin. Cv for CH4 equals to 27.84 joule per mole Kelvin. Cp for C2H6 equals to 53.11 joule per mole Kelvin. Cv for C2H6 is 44.80 joule per mole Kelvin. So now I am just solving this problem. So here we are dealing with the mixture of CH4 and C2H6, and now in this problem it is mentioned like it is a reversible adiabatic process. So for reversible adiabatic process we have a governing equation, that is PV to the power gamma equals to constant, and in terms of temperature and pressure we are having one more relationship, T2 by T1 equals to P2 by P1 to the power gamma minus 1 by gamma. So for T2 we have to find out T2, that is P2 by P1 gamma minus 1 to the power gamma into T1. So for this problem P2, P1 and T1 is given, because in this problem it is mentioned P1 is 1 bar, T1 is 300 Kelvin and P2 is 10 bar. But gamma Here we know gamma for air is 1.4, but here we are using a mixture of CH4 and C2H6. So we have to find out gamma for this mixture. So gamma for mixture. We have to find out gamma for mixture. So gamma is nothing but ratio of Cp and Cv. So we have to find out Cp for mixture. So now we can find out the mixture Cp for mixture Cp. In mixture we are having 25% of CH4. So Cp of mixture is 0.254 into Cp of CH4 plus 0.75 into Cp of C2H6. So Cp of mixture 0.25, Cp of CH4 is nothing but 36.65 plus 0.75 into Cp of C2H6 is 53.11. So Cp of mixture is 48.87 Joule per mole Kelvin. That is Cp of mixture. Similarly, we have to find out Cv for mixture. Cv for mixture, similarly Cv equals to 0.25 into Cv of CH4 plus 0.75 into Cv of C2H6. Here Cv of mixture 0.25, Cv of CH4 is 27.84 plus 0.75 into Cv of C2H6 is given 44.80. So the Cv of mixture will come 40.56 Joule per mole Kelvin. So now we are having Cp of mixture. Now we are having Cv for mixture. With the help of Cp and Cv we can find out gamma for mixture. Gamma for mixture. Gamma equals to Cp and Cv. Cp we have calculated 48.87. Cv we have calculated 40.56. So this ratio will come 1.2041. So now we have calculated the gamma, that is 1.204. Now we can apply our equation T2 equals to P2 by P1, gamma minus 1 by gamma into T1. In this problem, T1 is given 300 Kelvin, P1 that is already given, that is 1 bar, P2 is already given, that is 10. Now if we are plugging this value here, 10 by 1, 1.2049, that is gamma for mixture minus 1 divided by 1.2049 into T1 is 300. So T2 will be 300 into 10 to the power 0.2049 divided by 1.2049. So this value will come 443.78 Kelvin. So the correct answer is 443.78 Kelvin. The problem, I am just writing the problem. It's a theoretical problem. So first I will write the problem and I will give the solution. The stream of mass mkg is made to enter a combined separating and throttling calorimeter if after some time m1 kg is M1 kg is separated and M2 kg is throttled. M2 kg is throttled. Then dryness friction. Then dryness friction after throttling is found out is found out to be x2 Find the initial dryness friction. Find the initial dryness friction. So this is a theoretical question based on separating combined separating and throttling calorimeter. So I will just give the formula for our understanding. You just remember this formula, and whenever it is required you can apply this formula. So the initial dryness friction. So the initial dryness friction we can find out. Suppose we can take initial dryness friction is a solution. Assume initial dryness fraction is x1. So for x1, remember this thing x2 m2 divided by m1 plus m2. So this one is the formula for initial dryness friction, which is a function of dryness friction after throttling and total mass, that is m1 and m2. So x1 equals to x2 m2 divided by m1 plus m2. So by this formula you can easily calculate the things if the problem is based on combined separating and throttling calorimeter.